students, welcome back to your chemistry class. So till yesterday we had discussed about Bohr's model. Today we shall discuss why Bohr's model was failed. Though we had studied about his limitations, but still today we are going to further discuss about why his model had failed. To begin with, we will start with the de Broglie's hypothesis, which explains the dual nature of the matter. Louis de Broglie, he was a French physicist. He in 1924 advanced the idea that like photons, all material particles such as electron or proton or atom or even a molecule, a piece of chalk or even a piece of stone or an iron ball, whether it is a microscopic object or a macroscopic object, they all possessed dual character. What was that dual character? That a wave associated with a particle. Okay, this is called as a matter wave, or it is also termed as de Broglie's wave. So let us understand the de Broglie's relation. The wavelength of the wave associated with any material particle was always calculated by analogy with the photon. How? Like in case of photon, if it is assumed to have wave character, okay, if it is assumed to have wave character, then E is equal to hv. This was given by Planck's quantum theory. Okay, Planck's quantum theory is not in your syllabus, so I'm not going much into detail, but according to Planck's quantum theory, what did it say? That light always exhibited wave character. Okay, now let me take this as equation 1. Over here, if you see, where the E is equal to the frequency of the wave, and what is h? H is your Planck's constant. This we have been studying since yesterday. Now, if a photon is supposed to have particle character, now who gave this theory that it has a particle character? Then its energy is given by E is equal to mc square. Who gave this? This is a second equation. It was given by Einstein. Okay. So over here, if you see, where m is equal to mass of photon, right, and your c is the velocity of light. Okay, so from equation 1 and 2, what do we get? See over here, E is equal to h into frequency or Planck's constant into frequency of the wave. Here energy is equal to mass into velocity of the light square. So we can say that hv is equal to mc square. But velocity, what is it equal to? C upon lambda. The over here lambda is what? This is your wavelength. Okay, here this is equal to wavelength, right? Therefore we can say that h into, what is this V? C upon wavelength. C upon wavelength, this is equal to mc square. Or we can say that wavelength is equal to h upon m c. C and C gets cancelled. So wavelength is equal to h upon mc. This is your equation 3. Okay. De Broglie pointed out that this equation is applicable to any material particle, whether it is big, whether it is small. So if we assume that, let me rub this third equation over here, where wavelength was equal to Planck's constant upon mass into the velocity of light. Okay, so de Broglie, he pointed out that this equation is applicable to any material particle, whether it is big or small. So let if m is equal to mass of material particle, okay, and your v is equal to the velocity of a moving particle. Okay, so by putting value of m and v, right, what do we get in this equation? If I put the value of m and v, what do we get? Then the wavelength is equal to h upon m into v, that is the mass of material particle into the velocity of the moving particle. Okay, and we also know that momentum of the particle is equal to mv. Therefore we can say lambda can be equal to h upon p. Okay, so over here you can see where p is equal to the momentum of the particle, which is equal to the momentum of the particle, right? So this equation is called as de Broglie's equation, right? Now what is the significance? Although de Broglie's equation is applicable to any material particle, but it has certain significance only in case of micro particles. Though, as I told you, his hypothesis tried to explain both for the macro as well as micro objects or substances or particles, but significantly this is possible only in case of microorganisms. For example, suppose if you see a cricket ball, right? So that is also a material. So when it is thrown, then it does not move in a form of a wave. It moves only in a form of a particle, not in a form of a wave. So here his theory gets contradicted, right? So let us do some numericals to make ourselves understand why it happens. So suppose a cricket ball has mass equal to how much? Let it be say 150 grams, okay, and it is thrown with a velocity of say 2500 centimeter per second, right? So what will be its wavelength? Then wavelength is equal to h upon mv. Okay, now we already know what is Planck's constant value. It is 6.626 into 10 to the power minus 27 upon what is the value of m given to you? 150, and velocity 2500. If we calculate all this, what do we get? We get the answer as 1.767 into 10 to the power of minus 32 centimeter. Now this wavelength is very small and it cannot be measured easily. Thus, it may be concluded that although large particles like your cricket ball is also associated with a wavelength, but it cannot be treated as a wave. Why? Because its wavelength is not in the measurable range. Hence, I hope you have understood that it is meaningless to impose the wave nature on large particles. It is only imposed on micro particles, right? The ball should only be described over here as a particle, but it cannot be a wave. It cannot work as a wave. Clear? Now let us talk about a wavelength of an electron. We already know that the mass of electron, mass of mass of electron is equal to 9.108 into 10 to the power minus 28 grams, right? And its velocity is roughly equal to how much? 2.19 into 10 to the power 8 centimeters per second. Okay, what are we talking about? We are talking about here the wavelength of electron, and here we were talking about the wavelength of the cricket ball. Okay, so we are comparing the two. This is a macro object, this is a micro object. So which one is going to show the dual nature, the macro or the micro? We have already understood with the macro one that this cricket ball can be only considered to be a particle but not a wave. Now we are discussing to find out whether electron could be considered as a wave and as well as a particle. So let us understand first to find out the wavelength. So mass is given to you, velocity is given to you. Now let us find out the wavelength. It is equal to h upon mv. H we know 6.626 into 10 to the power minus 27 upon what is the mass given to you? 9.108 into 10 to the power minus 28 into V is given 2.19 into 10 to the power 8. Clear? All this will approximately come out to be 3.32 into 10 to the power minus 8 centimeters, right? Which will also be equal to 3.32 Armstrong. So over here what do we see? The wavelength is measurable and it is comparable to the wavelength of the X-rays also. Thus an electron can be associated with a wavelength whose value is still meaningful. Here the value was meaningless, but here it is meaningful. Hence an electron can also be treated as a wave, and so we say that an electron acts as a dual nature. It is a particle and it also acts as a, or it is also treated as a wave. Now since electron, it possesses both mass and the measurable wavelength, it should always be regarded thus as a particle and as a wave also, and hence as I have been telling you, it exhibits dual nature. Okay, so this wave nature of this electron, it has been utilized in the construction of your electron microscope, right? Now we are going to talk about Heisenberg's uncertainty principle. I hope till here everything is clear. So now let us study the principle which contradicts Bohr's theory, that is your Heisenberg's uncertainty principle. According to him, the position and the momentum of an electron cannot be exactly determined simultaneously. What did he say? I'm writing it down over here. According to Heisenberg, according to him, the position and momentum of an electron cannot be exactly determined simultaneously. Okay? Is this point clear? Now, mathematically, let us express this. According to him, if we denote over here, I am writing x as the position, right? And px is denoted as your momentum. Then delta x can be termed as uncertainty in position, and delta px will be what? Uncertainty in momentum. Okay, then delta x into delta px is always, remember, a positive value. Okay, it is always a positive value and can be equal to h upon 4 pi, where what is h? H is your Planck's constant. Once again I say delta x into delta px. What is delta x? The uncertainty in position into the uncertainty in the momentum. It is always a positive value and it has a minimum value which is found to be h upon 4 pi, where, as I said, h is your Planck's constant. Now we know that momentum is equal to mass into velocity, isn't it? So px is equal to what? M into vx, mass into velocity. Let's expand this formula. So how can we write down this? Delta x into delta x into what is delta px? Px is equal to m into vx. So we can write down m delta vx. Okay, this will be always have a minimum value of how much? H upon 4 pi. Followed? Thus we can say that delta x into delta vx is equal to h upon 4 pi if we bring m over here. Hence, smaller the mass of the particle, greater is the magnitude of the uncertainty. Okay, I repeat, I also write it down over here. Smaller the mass of the particle, okay, greater is the magnitude of uncertainty. I hope that till here it's very clear. Moreover, if your delta x, that is your uncertainty in the position, is very small, that is the position of the particle is known more or less exactly, and your delta v, that is your uncertainty in the velocity would be large, that is uncertainty in the determination of the velocity will be very large. Similarly, if an attempt is made to measure exactly the velocity of the particle, then the uncertainty with respect to the position will be very large. Thus, electron is a very small particle having almost negligible mass as 9.108 into 10 to the power 28 grams, that I had also written over here. Hence, the uncertainty in the position and the velocity for this microscopic particle, that is electron, is always expected to be very large. How can we say so? let us do the calculation and understand over here. Like delta x into delta v, it is equal to what? H upon 4 pi m, isn't it? So let's put the value of h. It is 6.626 into 10 to the power minus 27 upon what is 4 into pi is 3.14 into what is the mass of the electron, 9.108 into 10 to the power minus 28, and this approximately comes out to be, sorry, this should have been here also. So this is equivalent to 0.579 ergs second per gram. So this value is very large as compared to the dimensions of the characteristic quantities of the electron, and this cannot be neglected. Hence, we may conclude that the position and the velocity, or what we call as momentum of an electron, can never be determined simultaneously and accurately. So with this we wind up today. We have finished Heisenberg's uncertainty principle and de Broglie's equation. Thank you.